This is going to be an aerial refueling problem. I have some acknowledgments, some people that inspired this exercise. So there are lots of aircraft that do aerial refueling. A couple of them are KC-10 and KC-30. To be clear, this is not an analysis of one of those aircraft. There are lots of changes and simplifications due to time constraints. It's just inspired by history and things that we've learned about aerial refueling. So here's one of the pictures. This is basically an A330 made into a tanker aircraft that is refueling an F-16. In case it's not clear to you, that is the boom. We're going to talk a lot about the boom. An expert in aerial refueling says, flying a boom is just like flying a glider behind the tanker. You have full control authority, up, down, left, right, extend, and retract. It can extend 23 feet out, up and down, left and right. Here's another picture of that boom. You see the control surfaces? That's how you move the boom. So it really is like flying something, flying a little mini aircraft behind the tanker. This boom is massive. The thing, let's say it is designed to mechanically disconnect at 5 tons of tension. And that means it can withstand that amount safely before it needs to disconnect some massive forces. If you break off a boom, this is a pretty serious event. Here it is, a KC-30 refueling a B-1. Of course, the boom has to drop down, the aircraft has to fly up to it, and you get your fuel. We'll talk about more details in a few minutes. Let's start STPA. You already have enough information, even if you've never heard of aerial refueling. You've probably heard of it, but may not know much about it. You already have enough to start step 1. So you can start this process incredibly early. What are some losses for this aircraft? Well, we mentioned some before and they all still apply. What about loss of life? What about damage to the aircraft? What's a mission loss here? Maybe some loss of the refueling mission. Some hazards we might talk about, well, the same ones that we had from before. Many of them still apply too. What about aircraft gets too close to each other? Now the separation might be different for refueling. You're obviously getting a lot closer than 3 nautical miles, which is a standard for many areas. The airframe integrity is degraded. If we're impacting the airframe and causing some weakness there, we're not having a good day. So we might have a number of hazards like that. I think those are not too tricky for you to catch because they're similar to what we had before. And I want to focus more time on the later steps. So we've got modeling the control structure. There's a specific area that I want to get to, but I've got to take a step back and show you that there's really a whole development process here. If you're familiar with the systems engineering V model, there's a lot of iteration. STPA really starts way up front at the beginning when you're figuring out the whole concept of the operation of this thing, all the way down to detailed design, implementation, and then on the other side, when you're doing testing, verification, and validation, there is a spot where STPA can support development in all of these phases. Compared to the very first phase, the control structure may grow and evolve, and you may zoom in and expand on areas as you learn more about the system. So you might start with something super high level like this, from Nancy's book. We can go all the way up to Congress if you wanted to look at company management and those interactions. You might eventually, or zooming in to look at mission planning and real-time operations. Of course, we've probably got to have some kind of communication between the tanker and the receiver. How is this going to work in real time? How are we going to plan for these missions ahead of time? What kind of procedures are we going to provide? That's an interesting control loop. If procedures are wrong, and sometimes they are, why? They may have had the wrong process model. They may have had the wrong decision-making process, the wrong feedback to make decisions. And the same is true for operations. So you might get something like this. We're going to dive in a little bit more. Let's take that guy on the right-hand side and zoom in there. There's some interesting interactions between the tanker and the receiver. You might think, hey, can we have centralized control of this thing? It turns out that's not really practical. Those two aircraft are going to be right next to each other. They may be able to see each other. It doesn't really make sense to introduce such a time delay to go through a third party who can't be there, can't see what's going on. So we need some kind of interaction directly between these. This is a common way that works. The tanker aircraft starts by introducing some movement, and ideally it's not moving at all, it's going in a straight and level line. But if it does move, the receiver needs to know about it and may need to respond. The next arrow down, we've got receiver does something. The receiver is also flying the aircraft, but it's tracking tanker movement. That's its job. Its job is not to fly in a straight line because it may diverge from the tanker. Its job is to maintain a fixed distance from the tanker. This is called gross tracking. Now, this isn't perfect because you're a human being, you're flying an aircraft, although it's changing now. Let's say that that's the case. The tanker has a boom on it, and it has the ability to move the boom to a receptacle. This is called fine tracking. It lines the boom right up and starts delivering fuel. If needed, you might need a mechanism to provide verbal movement guidance back to the receiver to get this gross tracking to adjust in a certain way. This is a super high level of the interactions between these aircraft. This is not where we're going to look in this exercise. We're going to go one level further. We're going to take this tanker aircraft and peel back the onion and look at what's going on inside there. It's actually really interesting. There's a whole control structure inside the tanker aircraft. So for the purpose of this exercise, that's where I want to look. I have a lot of information that we can discuss publicly and have a good exercise. That's the reason. Normally, we wouldn't just put this control structure and do this analysis. We would start way back here and come up with higher level requirements, higher level constraints and scenarios to try to mitigate. But just in the interest of time, this is what we're going to spend most of our time on. So what does this look like inside the tanker? Let's look very carefully at how the boom is controlled. So on a KC-30A, this is what the refueling control station looks like. Again, we're not analyzing any one of these aircraft. I'm just giving you some examples so you have a frame of reference. Generally, you may have a primary operator on the left. You may have an instructor on the right-hand side. Another phrase for the boom operator would be the air refueling officer. I'll just use boom operator for most of these slides. What are they looking at here? Well, in this aircraft, they've got a video feed, and there's one of their controls. It's the boom flight control stick. Controls position of that boom. All right, there's a lot of information still missing. I've just given you about 3 circles. Do we have enough to sketch a control structure? Let's give it a shot. What are we controlling? What do you think a control process might be? Hey, look at that. Folks are getting used to this. So for this application, we are looking at the boom. Let me draw that. All right, next question. What controllers or decision makers might be in this system? Now, I haven't told you a whole lot of information about this, so you may have to propose some. But what do you think we might include in the control structure? Yeah. So we've got ARO. Fantastic. And there are a lot of humans besides the ARO. Are there any non-human controllers in this system? We haven't said much about it, but there might be some digital electronics. That control stick is an electrical control stick. It probably sends a signal down to some digital hardware that may have some filtering, may be making some decisions, may have some different modes. Let's throw that in there. And let's keep this simple for now. Let's say that this boom control unit, this is horrible, handwriting. Let's say that this boom control unit is really dead simple. It basically just does what the boom operator says to do. Just implements the control actions directly, let's say. All right, let's figure out who or what controls the boom. I think that's pretty obvious. What kind of control actions could we send to the boom? Yeah, we've got different variations of movement. We could say X, Y, Z, or something to that effect. Well, we've got these movement commands. What do you think the ARO is commanding? Well, the ARO is also commanding a boom position. Via the stick. All right. Do you think there might be some other supervisory control action like we had before for this piece of electronics from the operator? What else do you think the operator, I didn't have a question prepared for this, I just noticed, but what else could the operator maybe provide? Yeah, how about turning the electronics on or off in an emergency? That might be important. Boom control unit on, off. Yeah, I think we'll just start there. We'll just keep it that simple. Now, what kind of feedback, let's look at those control actions for the operator. What kind of feedback should the operator have to do their job, to figure out where to direct the boom? Let's start there. Visual feedback, that's right. So maybe some of that comes directly from the boom through just a camera. Maybe did you see any data on the screen? If you didn't, maybe we should put some there. Maybe what kinds of information would be useful that might be calculated by the boom control unit? What's the load on the boom? Loading, position, you got it. If you've ever used this kind of joystick, there's what they call a feel in the joystick that can be very useful for controllability. Maybe it provides some kind of synthetic feel. All right, and we can, oh, I didn't put the video. Perfect. That's probably some feedback going up to the boom control unit. So what is this digital hardware going to have to measure if we're going to help the ARO do their job? Well, we're going to have to measure all those things, right? We're going to have to measure boom position. We need some kind of sensor to measure load, X, Y, Z. All of these are pretty much 3 dimensions. All right, or more. Fantastic. All right, we've sketched what I wanted to. Fantastic job. Here's a polished up version. We'll get back to that upward arrow in a minute. This is another common pattern. It's not a rule, but it appears all over the place. We've got automation in the middle, humans at the top. By the way, even in a fully autonomous vehicle, you still have humans at the top. Who's providing the destination to the car? The car doesn't decide what the destination is. The human decides the destination, or maybe other control actions besides that. What if the human decides they want to get out, they want to stop, they want to abort the ride, or whatever it is? So there is generally always a human somewhere in the system, even for fully automated systems. We may, if you didn't already identify it, we would have to add maybe some direct interaction with the boom. Somebody might say, hey, should we control the boom directly? What if the digital hardware has to be shut off? What are we going to do? Are we just going to land a plane with that thing hanging out? Maybe we need some kind of cable. It's kind of hard to do for systems like this, but we might look at some options and see what kind of controls we can put in place. Remember, we're going to be looking at the context of this system, or the communication we have with tanker pilots, receiver pilots, communication maybe from controllers up above. Here's the feedback. You're already ahead of us, ahead of me. You already got this feedback. We need maybe contact sensing. We may need to know if it's made contact, if we're going to be turning fuel on or off. That's another control action we could add. And we could very quickly end up with a very detailed control structure like this before we're done. We're not going to do that. That would be a further iteration we're not going to get to. I want to keep it simple for this exercise. We're going to just look at a 3-box control structure, focusing on the boom operations for the purpose of this exercise, because I have some material that we can use in the public domain to look at that interaction. All right, so I haven't even shown you what the video screen looks like. I just showed you that there is one. Let's compare to what you just proposed to an actual implementation. Well, we've got a telescope extension over there on the right. We've got vertical and lateral degrees from trail. Think of trail as kind of a home position for the boom where the forces are low. It just kind of wants to hang there in trail. There's maybe a state of the receiver where the boom latches onto. There are boom loads that we may want to sense. There's maybe a flight control mode. Are we hooked up to the aircraft or not? Perfect. This is pretty close to what you proposed. Here's our control structure. We're just going to freeze the control structure for a moment. We're going to analyze this and work from here. So let's say that this is a very dead simple system. You just move the stick and it moves the boom. And then someone comes along and says, hey, I've got an idea. Let's make a computer digital upgrade. Here's the old system. There are basically two modes. There is a free flight mode and a coupled mode. Free flight mode, you're moving the boom into position. Coupled mode, you're moving it as needed to minimize maybe contact loading. Very manual concept. And the decision is we're going to automate some of this stuff. What are we going to automate? Well, one of the hard parts here is when it's coupled, we've got loads that are changing very quickly. So we need to do something called a load alleviation, is the proposal anyway. So when the boom is coupled, they want to automatically fly the boom by computer. The operator does nothing. It's going to use some sensors to detect the mechanical forces on the boom. This is when it's coupled and connected, and it's going to automatically move the boom to always minimize and zero out those forces. So the new partially automated boom control, by the way, these days they have fully automated. Just in the last few months, there was a demonstration, but let's go with partially automated. And we've got two basic modes, let's say. Mode one is free flight. Boom operator is controlling it. It's a very manual concept, and you fly the boom to insert it into the receptacle. Phase two is the coupled mode. The trigger between these is when the BCU, the computer, senses a positive contact, and it enters this coupled mode, and it automatically flies the boom. The boom operator is not in control. The stick is in fact ignored, and it has to be because the operators are not flying the thing anymore. And the system senses tip loads and flies to null out that load. What can you do when you're in mode two? Well, the operator or the receiver can command a disconnect, let's say. If you didn't follow all these details, don't worry. These are more details than you actually need, but some software folks like to have a frame of reference. There is one more control that we need if we're going to have these two modes, is we need this toggle mode button or some way to exit the autonomous mode. Maybe go back to manual control, but we're going to keep the control structure almost the same. Look at this. I mean, what actually changes in here? The code and the behavior inside the guts of the BCU has changed quite a bit, but the control structure has not changed that much. The boom operator can still command manual boom position. It just might be ignored now in some situations. It can still command the BCU on or off. There is still control surface movement. The sensors are all the same. What did we add though? We did add one new control action for the boom operator to toggle the mode command of the boom control unit. So we may need to exit the autonomous or automated mode. All right, so let's go to step three. This is where we're going to spend most of our time, the rest of the analysis. I wanted to try to get to this point quickly so you can get some practice with unsafe control actions and scenarios. So let's go to step three. Let's analyze these control actions and see what we get. Let's start with the BCU off command. This is provided by the boom operator. Do you remember the 4 ways a control action can be unsafe? What if it's not provided? What if it is provided? What if it's too early or too late? What if it's stopped too soon or applied too long? Remember I talked about subcategories in that second column there? Some things we might want to think about is what if it's provided in the wrong situation? What if it's provided excessively somehow? Is that possible? Do we care? Can it be provided insufficient in some way? Can it be repetitive? Can it be provided in the wrong direction? These might be interesting cases to consider. When we construct a UCA, you can see the elements of a UCA right there, the source controller, the type of control action. So if we read this out, it says boom operator provides BCU off command when nothing's wrong. When the thing is operating normally, it's doing automatic load alleviation, it's keeping those loads low, and we go and turn force off. We pull the plug on the BCU, that boom goes dead. That may cause some problems for us with the receiving aircraft if the boom is coupled. So that might be an unsafe control action that we need to consider. That would go right here in the middle column. I want to just throw that up as an example. I actually want to look at that first column. Fill in the blank for me for a new UCA. When might it be unsafe not to provide the BCU off command? Yet the forces on this boom could potentially be very huge. Both the forces that are felt and sensed if we're in the airstream, and the forces that are commanded are very powerful. So it is physically possible that this boom could be damaged by erroneous or unsafe commands from the BCU. So if that thing starts malfunctioning, or if it starts sending unsafe commands, our only chance here is to turn off the BCU. You've got it. There's more than one, again, but I've seen this expressed in a number of different ways. Here's one way to phrase that. When the BCU is providing movement commands that exceed some structural limits, and we can figure out what those limits are. If that's happening, you need to turn that thing off right away before it causes serious damage. All right, let's look at the movement command. So this is a different command. This is the manual command to grab the stick and move it around. Is there a way that providing manual movement commands can get us into trouble and cause one of those hazards like damage to the aircraft or the fuselage potentially, or the boom? You're going fantastic, by the way. Look at all those answers streaming in. Let's do this. Let's look at two different cases where this could occur. Case one, let's say the boom is in contact, and then we'll look at case two later. Let's start with case one. If the boom is in contact, is there any way you can provide a manual movement command to cause damage? Worst case. When is it dangerous to provide movement command when we're in contact? And think about those keywords there. Is there a way that you could provide the manual movement command? Yeah, potentially all of them. What if we provide a manual movement command that's excessive when we're coupled to the thing? Could we maybe forcibly break the boom off while it's attached to the receiving aircraft? Potentially, we certainly don't want that to happen. That would count as an unsafe control action. So you could use slightly different words if you want, but this is the meat of the problem. If you provide excessive manual movement commands greater than some limit, when the boom is in contact, you can potentially break the boom. Now, folks have been paying real close attention, or maybe have used this before. You might say, but wait a minute, if you're in contact, the BCU is going to ignore the stick anyways. So why do I care? If you were to propose that, I would say, let's ask the safety folks in the room, are you comfortable with that. Do you really want to tell these operators, go ahead and push the stick full up and down while it's coupled? Trust me, the BCU is going to ignore your movements. Or should we just consider the worst case and say, hey, you know, hopefully it doesn't listen to the stick movements, but you know what? Don't go pushing it full up or down while it's coupled anyways. Of course, we would do the latter. So this is an example of a worst case consideration. We do that constantly in STPA. We never consider the best case. We don't try to focus on the most likely case. We are always looking for the worst case because that's going to get us to the requirements we need to make sure these systems are working and to produce the procedures we want to make sure all these systems work. So you've got that one. What else? Let's see. What about case 2 when the boom is not in contact? Is there a way to provide a manual movement command when we're not in contact with an aircraft that causes some destruction? Fantastic. Absolutely. So in both cases, when we're in contact and when we're not in contact, there are ways we can cause damage. The limits might be different. The movement that causes a problem might be different in those two cases, whether we're in contact or not. But both of those are valid cases for UCA. All right, just to remind you, what we did so far is we looked at how not providing the VCU off command can get us into trouble if the thing is moving erratically, and for sure that's a problem we've got to prevent. Another case is if we're in contact or not in contact and we provide these manual commands. As an operator, we can create some problems. Now let's look at the VCU itself. You could think of this as digital hardware or computer software. Now let's fill in the second column. How can movement commands from the BCU get us into trouble? You might think about those same categories and think about those same cases. So let's start with case 1. Fill in that second column then. Fill in the UCA for me. Let's say we're in contact. When is it dangerous to provide a movement command when we're in contact? Fantastic. Yeah, for sure. First one that comes to mind is you provide excessive movement. Just like the boom operator, if the BCU does it, that's a bad day too, because you can really break the boom by doing this. What are some other ways? Well, what if you provide this movement command when we really shouldn't be moving the boom at all, when the load is within some tolerance, when it's already low? If we move the boom, we're going to be increasing the load and making things worse. We might think of some other cases in there. What about case 2? What about when we're not in contact? What are the conditions where providing movement commands and we're not in contact are going to create a problem or lead to a hazard? Well, I think you've got all the answers, so we'll just cut to the chase here. What if the BCU does this? Now remember, we're not in contact. This thing is supposed to be slaved to the operator. So if we're not in contact and the boom operator is not moving the stick, we're just spuriously moving the boom, we're causing a problem potentially. What if we move the boom when we've been turned off, maybe due to some kind of malfunction? That's a problem. Of course, we could do it in the wrong direction. There are some interesting cases where the stick was wired up in reverse order during maintenance. That's a very difficult problem to resolve in real time. Can't remap your brain very easily to just reverse your control inputs. What if we provide excessive movement commands beyond the mechanical boom limits and so on? We would look at timing. What would make the movement command too late? Well, if it's too late after the boom operator moves the stick, and we could come up with a specific criteria on that. What about too early? Well, if any time before we see a stick movement, that's what might make it too early. What about too long in the last column? Applied too long. Look at the middle UCA there. The VCU continues providing the movement command too long after the boom position exceeds some amount. We corrected for the position, we nulled things out, and then we just continued. We could also look at the extreme limits of the boom capability. If we push it hard over to the edge, maybe we could cause some damage there. All right, so we'd be looking for UCAs just like this. Let's move on. I didn't even have to show you this slide. Some folks like to work with timing diagrams. This is one way to see the differences between the different columns in a UCA table. That second column, providing the UCA, there are different ways that providing could get us into trouble. Some of them may be excessive, insufficient, wrong direction. But column 3 is adjusting something else about the control action. If it's adjusting the rising edge, providing it too early or too late. In commands that have a duration, it's also reasonable to talk about a falling edge or how long the thing was asserted for. That's column 4. In case there was any confusion there, that may help to clear it up. It's another way to think about it. All right. I hinted that we would look at formal STPA. Now notice what I did in these tables. It didn't quite, not everything fit on a slide. So what I did here is I broke things up into 2 cases. I say, what if the boom is in contact? And we wrote all the UCAs here. And I said, what if the boom is not in contact? Now this is equivalent to just putting all these UCAs together and saying when the load does not exceed TBD and it's in contact. And on this slide, it's the same as saying when movement command is in wrong direction and it's not in contact, meaning we're looking at the stick direction. The stick direction matters only when we're not in contact, right? So it's a way to think about the problem in terms of variables and states that really matter for the control action. What we can do is take those states and represent them in a table. This is one way to formalize this part of STPA. So every row in this table represents an unsafe control action. This is a machine readable format, but we can read it as well. So the first row here, you say the source control is the BCU. What's the control action we're talking about? The movement command. So BCU provides a movement command in what context? Let's say we're in contact with the receiver and the movement is above some high limit. The strength of movement. If we're in contact and we're above the high limit, we're in trouble. This is unsafe to provide. Yes, that's one of our UCAs. What about this one? BCU provides a movement command when we're not in contact, we're above the high limit, and we're matching stick movement. This is okay in manual mode because we allow more movement in manual mode than when you're fixed to a receiving aircraft that's in a fixed position and not moving about erratically, let's say. All right, next one. What about BCU provides a movement command when the movement is greater than the high limit. It's way out there. These two don't even matter. Anytime you're outside the high limit, you're potentially about to cause damage. This is going to be unsafe to provide. So these stars can be seen as don't care terms. They match with any stick movement and any state of boom contact. It just consumes everything else. Here's the last one, and there are more. This table's not complete. This is just demonstrating how to represent UCAs. A BCU provides movement command when boom is not in contact and there is no stick movement. So if we're not in contact, we're slaved to the stick's not moving anywhere, and we send these spurious movement commands, that's no good. This is unsafe to provide. There are some neat things we can do with this table. We can look for conflicts. We can automatically generate some executable requirements for the digital controller. But I think I don't want to focus on this. I just want to throw that out there since there were some questions and some interest in it. Let's go back to the human readable version of the control actions. And let me show you something else. These slides get pretty cluttered. So I told you every single slide is going to be a simplification. It's just trying to make one point or another. If I showed you a completed analysis, it'd be many, many pages and we wouldn't be able to read it or present it. So one of the things that I've done is there's so many UCAs, they don't on a PowerPoint slide have these tags and traceability. But before you're finished, you need to add tag ID numbers. Usually I do this at the end because otherwise you're just renumbering them constantly when you find a new UCA. And you've got to trace them back to the hazards. So we have full traceability in every UCA, even if it's not on every single PowerPoint slide. The other thing is these trace forward to drive requirements and other things like potentially test scenarios. So here's a requirement that comes directly from UCA 10. BCU must, shall provide movement command within TBD seconds after boom operator moves stick and when not coupled. So if we're not coupled, anytime you move the stick, we have to move the boom immediately. That's what that requirement says. Why do we have that requirement? Because anything else would lead to this hazard as per UCA 10. Now, what do we get from a test case? We don't just write a requirement down and assume and trust that it's always going to be met. We create test cases. Now, the important thing in test cases is how do you come up with important test cases? We know we can't test everything, every possible combination. We'll be here for maybe a decade to do that. So we've got to pinpoint the most critical cases to test. What are the most important cases to test from a safety standpoint? The ones that are unsafe, the ones that lead to a hazard or a loss. So we can derive these from the unsafe control actions. Now, in the UCA table, we don't have every possible control action listed in every possible context, just the ones that are unsafe. So we can derive test cases. Here's a test case for this guy. The context that you need to set up or simulate or actually create. The boom is coupled and the boom operator moves the stick. And in that case, we need to verify that the BCU does not, does provide movement commands that match the stick, and they have to be within TBD seconds. And why? Because that comes from UCA 10. If we want to prevent UCA 10, we better enforce that requirement, and we should probably double check and do testing as well. All right, here's another one. Let's look at the second column. BCU provides movement command when boom operator does not move the stick. Well, the requirement is must not provide. Again, I fully understand some of the difficulties with shall nots and must nots. You can call this a safety constraint if this helps, but these are really useful to designers and engineers in a lot of ways. This is very useful information to know. If these things happen, we have to design the thing so that it doesn't provide these movement commands. The test case we get out of this, we want to set up a context where the boom is coupled and the boom operator does not move the stick, and we need to be verifying it every time we're in that context. The BCU does not provide the movement command. It comes right from UCA 2. We're verifying really with a test that UCA 2 is not being provided as far as we can see. Now, I'm not making an argument that we can prove all tests. I am fully aware of the limitations of testing, but no one's going to argue we should not do testing at all. We should do something, and this is something we can look for throughout our test cases. Another point to make, this UCA table that we were constructing, I was framing this very much in the mindset of safety, but was it really safety? How many of these would be attractive targets for an adversary to trigger? All of them. These are exactly the things an adversary would like to find a way to trigger or to inject or create. These are the ways they're going to induce a loss. So there is no difference yet between safety and security. The UCAs are identical. Let's get to the last step to identify scenarios. Here's the loop. So we've got an unsafe control action. Can this actually happen in my system? Well, this is an unsafe control action you identified. BCU provides excessive movement command when we're in contact. Why is that bad? Because we can snap the boom right off when we're in contact with the other receiving aircraft. All right, let's see if we can put together a scenario. So I want you to identify some beliefs that would explain why the BCU would do that. Look at this. If you submit an answer, you should be able to see all the other previous answers. Exactly. There are multiple things here, but just about everybody is submitting an answer along the lines of, what if it thinks it's not in contact? If you didn't catch that already, one place to start, if you're stumped, is look at the context. If it doesn't know that that's actually the context, how is it going to prevent the UCA? So one of the beliefs is that it's not in contact. We're going to pursue that in just a moment. What other beliefs could explain it. Now, being not in contact by itself is not enough to move the boom. It has to believe more than the fact that it's not in contact. What else does it have to believe? So we're not coupled. What else does it have to think is happening in order to pass on a movement command? If it believes that the stick is moving and that we're not in contact, there you go. We're going to move the boom, aren't we? If you're the BCU. So let's look at both of these. You see this is a slightly more complex case than what we had before. So let's look at the last one. Let's look at how it can believe the stick is moving. Well, the stick could actually be moving. It doesn't even have to be a false belief. It doesn't contradict anything in the UCA. The operator could have actually sent a manual movement command when the boom is in contact. Now, we might have a procedure that's somewhere that says, hey, although you'll be ignored when you're truly in contact. By the way, see the UCA? This is the truth statement. We really are in contact. Otherwise, we don't care. So this is the truth. These are beliefs. Beliefs don't necessarily match reality. So we are in contact. The operator could actually send a manual command when the boom is in contact. Remember we talked about this? We said, well, you know, it probably would be okay for them to do because the BCU should be ignoring that, but no, we're not going to say that. We're not going to assume that. We're going to say just don't touch the control stick when we're in this mode because there may be some confusion or any number of problems going on. Just don't touch it. Well, if the operator does send a movement command, that's part of the scenario here. That will trigger half of the process model belief we need to get this UCA. So that might be a reason to go to whoever's creating the procedure in this system and say, hey, you know, I had a fuzzy feeling before that, you know, we probably shouldn't do this just based on my experience. But now, look, I'm building a concrete scenario, and half of the scenario is this problem right here. We really better bake this into the procedure, maybe give them some training, and maybe tell them what the problems are if you do this even when you're in contact and it's supposed to, the control stick is supposed to be ignored, why you shouldn't touch it anyway, because it's part of the scenario. Let's look at the other one. It also has to believe the boom is not in contact for this to work. Now there's other problems. We're going to look in a minute. We're going to look at how the thing could be designed wrong, and these aren't actually the things that were built into it. But let's start in this path. It believes the boom is not in contact. Now the next question we would generate is, how could the BCU determine the boom is not in contact? Well, if you ask that question to me or to someone who knows this system, this is what we would do in STPA. We'd have an interdisciplinary team. You don't have to know all the answers. You just have to know how to get the questions and contact the people with the answers. If you ask a subject matter expert this question, or even a test pilot, they would say, well, the way this works is the BCU has a pulse input from a sensor. And when you get a pulse, we toggle the beliefs. All right. So the sensor detects that we're coupled and it sends a pulse. It detects that we're disconnected, it sends the same pulse. And that toggles our belief. That's how this system is designed. I'm going to open a new question. Is this a good control algorithm? What do you think? Very few of you have said yes. Well, it's an actual control algorithm, so I don't have the rationale that was used when it was designed, but there's a rationale for this, I'm sure. But there are some weaknesses like with anything else. What kind of feedback could fool this control algorithm and cause the flawed process model that's highlighted? All kinds of issues. It'd be pretty hard to prevent all of these issues. Maybe we can, but we ought to look carefully at the design. Turns out One of the ways to do this, and you've already mentioned it, and you can see each other's answers. One way is if we get a double pulse somehow on contact. Could we bounce? Picture this. You've got two separate aircraft flown by separate human beings in the sky. Is it possible that you get a double pulse on contact? What will that do to this algorithm? You bounce once before you make and maintain contact. Well, that will cause exactly this problem. That algorithm will say contacted, not contacted. The belief will say the boom is not in contact when you are, and this scenario could very well happen. You've got it. Now, if you put all this together, remember we had two process model beliefs. If we don't have protection for this bouncing, or maybe a pulse feedback is missing somehow, or it could be delayed. There's all kinds of ways this could happen. If we don't have protection for these, and we don't have protection for operators who may find a way to move the stick during contact operations, we're in trouble. Let's say we currently have no control measure to handle this scenario. Here's a question for you. Let's not wait for this accident to happen. Let's pretend it already did. What kinds of control measures can you identify? Look at the whole spectrum. I think design features are often the strongest. So at least give me some design features that might prevent this scenario, but give me some ideas. What can we do about it? Great. I think we've got technical side covered. Give me some ideas about the non-technical side. What should we do in the procedures? What should we tell the operators? Maybe we should tell them not to move it when it's in contact, but should we tell them why? I think we definitely should tell them why. We should tell them this exact scenario. What should we do in training? Should we not just tell them, have them experience it? What about testing, putting the hardware on a test bench, or the system on a test bench, and getting this to happen? What about during flight testing, tell the receiver pilot, hey, we got this double pulse issue. We think we've got under control, but we ought to test it. Why don't you approach and maybe do a little double tap if it's convenient? I don't know. There may be a whole slew of things that we can identify to try to make sure we've covered this case. Is this case safety, or is it security? Well, I've certainly been framing it as safety, but wait a minute. How many of these would an adversary like to cause? All of them. Certainly if they can cause this feedback and they know that this weakness exists in the rest of the system, that would be a wonderful place for them to target. What if they can induce this belief somehow? What if they could take advantage of this control algorithm flaw? What if they can directly inject this unsafe control action? You don't even have to do any of this work to find that one. If we can directly inject this unsafe control action, we're in trouble. Would some of the control measures that you entered mitigate some of the security scenarios as well? I added the block down there in the middle, an adversary blocks or spoofs feedback indicating contact. Would some of your control measures have a side effect of handling that case as well? Yeah, they would, for sure. So look at this. It's only until that middle block in the bottom there that we finally saw the difference between safety and security. The rest of it was almost identical, the scenarios. The only difference is whether the cause at the end of the day is an adversary in our system, or if we did it to ourselves completely. I don't see why you would do a process like this for safety and then do it totally separately for security. You're repeating 90% of the results. Just either do it once and get both safety and security, or maybe bring your teams together, because maybe the security team can provide some new insights that the safety team didn't consider, and vice versa. All right, let's consider a different UCA. Let's look at the BCU, excessive movement command when not in contact. Remember, we just looked at the case where you are in contact, and we looked at a problem. Let's look at the other case, we're not in contact. So the BCU here provides excessive movement command when we're not in contact. So now we're not in contact, maybe there isn't even another aircraft nearby, and we provide these automated movement commands that are outside mechanical boom limits. What in the world would cause the BCU to do that? Fantastic. Yeah, for sure. If it believes the boom is in contact, we just looked at the opposite issue. This one may be just as important. What else? Now, believing it's in contact is not enough. It's got to believe something else in addition, and many of you have gotten it already. It's if it believes we're in contact, it doesn't just move all the time to the left when we're in contact. It responds to load. So it must believe that the load is excessive and we're in contact. If those two beliefs happen, we are in trouble. So we can generate a question. How would the BCU determine that the load is excessive? Well, you might go to a subject matter expert and they would tell you, well, it's actually very easy. You don't actually have to have excessive forces because the normal air forces on an uncoupled boom are very different than when you're coupled to an aircraft. If we're listening to the sensors when that happens and we're just dangling in the air, those load sensors will report large, random, and rapidly fluctuating loads. Oh, that's interesting. What's that going to do to the BCU? The BCU is going to try to zero out those loads. So that explains one of the process model flaws. That'll happen right away if we're listening to those load sensors. And by the way, the control algorithm to process the feedback and turn it into control actions for movement, the control algorithm doesn't have any filter built in. It's designed to always compensate for all load feedback anytime the boom is in contact. That's interesting. I think we're getting some scenarios here. All right, what about the other process model? Well, if it believes we're in contact, that's a problem. How can it believe that we're in contact? We covered this already. It'll believe we're in contact erroneously because of this pulse thing that's going on. If there's any way to get a double pulse or a missing pulse or a delayed pulse, look at this, we've got a common cause for multiple scenarios here. And we have no control measure to handle this case. So you see this case? This case has two process model flaws. It says if we believe it's in contact, and that can happen due to the way that pulses work, every pulse just toggles us. So if we miss a pulse, we're out of sync. And this can cause a problem by design because it's going to respond to air forces. As long as this signal is wrong, it's going to be reading in those sensors, and the design of those sensors reports random, rapidly fluctuating loads. So the design of this thing is such that we're going to be in trouble. All right, you already postulated some measures for the scenario on the screen, which is the double pulse problem or the missing pulse problem. Let's postulate some measures for this problem, the excessive load issue. What design measures could we use for this? So redundancy does solve a problem caused by a component failure. What if there's no failure in the system? What if it's just a bounce upon contact? We're going to have to make a design change too, not just to add redundancy. Any other suggestions? Can we change the algorithm somehow? It turns out if you ask an expert, they'll tell you these rapidly fluctuating load feedback signals, they look a lot different than you would expect to see if you're connected to a receiving aircraft. They look a lot different. Maybe we can detect that and say, hey, wait a minute, is this thing really connected to an aircraft if it's moving instantly from left to right in a millisecond? Probably not. And maybe we can determine that we're out of sync and have a different control algorithm. In other words, maybe we don't always want to respond to any load feedback when we're in contact. And even if you don't agree with that, with every change, there's other potential scenarios we have to look at, make sure we're not making things worse. Another option is maybe we should detect that and send an indication to the operator and say, hey, it looks like we're not connected. Can you confirm? Because if it's true, we're in the wrong mode. We need to exit this mode. Maybe prompt them so they have some idea what's going on, what the BCU is thinking. Again, this is safety and security at the same time. So we've got to look at the control algorithm. We looked at every which way the process model could go wrong. What's left? Well, what if the process model is not flawed? What if it knows the stick is not moving? It knows the boom is not in contact, and it provides movement commands anyway. Well, there's a flaw in the control algorithm then. And that's the nature of the flaw. We can write a requirement and show that if this is happening, the requirement is being violated. How could that happen? Well, maybe the algorithm was updated by an outside controller. By the way, is that safety or security? You think it's security, and it is, but it's also safety. If we build in an update mechanism, who's going to be updating it? Us, in addition. So we could update it incorrectly ourselves, not just with an adversary in the loop. Here's an interesting case. It believes the boom is in contact. How else, other than looking at sensors? Is there an operator command to force coupled mode? There might be. And that's another way we can come to believe we're in contact when we're not and provide these excessive commands. This is, again, safety and security. Another flawed process model. Maybe we incorrectly believe that the movement command is not excessive. Look at the underlying part of the UCA. How do we figure out if a movement command is excessive or not? It turns out it's not just a fixed constant that never changes. We have to do some calculations. So the generated question, just like all of the others, is how would the BCU determine if movement is excessive? Well, the way it does this is it compares the movement or the force to some specified limits for an aircraft type. It changes depending on the aircraft. All right. So how does it update the limits when you get a new aircraft? Well, maybe there's some feedback from the aircraft itself. Whoa, we just found a potentially major problem. You don't maybe even have to have access to the physical aircraft to cause some trouble with this system if we're really responding to and trusting this feedback from the receiving aircraft. Here's another issue. Another way to do this, if you're not receiving feedback from the aircraft, is to have the operator program those limits for the receiving aircraft. So the operator, the ARO or the boom operator may see the aircraft, say, okay, that aircraft, here's the book, look it up and type in the limits. That's another implementation of this. So that just shifts the scenario up above. Maybe the operator can set the wrong limits, and the BCU has no idea that these are excessive movement commands for this aircraft. This is kind of interesting because in some implementations, they just have a number that you type in, and that's the entire limit for the system. Now, really, it might have been a better idea to have a global limit for the tanker that's built into the BCU or the aerial refueling system. So there's no way that system is going to exceed the limits for the tanker itself. And on top of that, have some programmable limits for the aircraft. But there are implementations that don't do that. They just have a number that you type in, and whatever the number is what the system will allow, even if it's so high that it could destroy the boom on the tanker aircraft. Does that sound like a weakness? This is a very realistic weakness here, and we better think of these scenarios and identify controls. All right, I just want to look at a couple operator scenarios, and then we'll be done with this exercise. Let's look at the boom operator. So the boom operator provides manual movement command when the boom is in contact. Remember we said that earlier? We said if the boom is providing these commands, now maybe they might reason and say, well, it should be ignored if we're in contact. But why would they do this? Why would they actually think that this is a good idea to provide? Yeah, for sure. I mean, this is the first answer is the easy one, of course. They believe it's not yet in contact and they're trying to get it into contact. All right, that one's done. What else do we have? Yeah, they could believe that it's ignoring the stick like it's designed to do. So why do I care? It's supposed to be ignoring my stick in this mode. What else could they believe? I almost want to underline the word excessive up there. Yeah. Maybe they believe it's not excessive. The movement is normal. How would they actually know if it's excessive? They have an indication of the load forces, but do they have a quick indication of when the force exceeds some limit and a procedure in place to transition or turn off the BCU in that case? So here are 3 modes we might look at. Let's take that middle one. Why might they believe the BCU is in coupled mode and therefore ignoring manual commands when it's not? Well, what if they see the boom make contact, but the BCU didn't sense it? So the BCU actually did not change modes and is still listening to manual commands. Hey, we actually found earlier that that's a very realistic scenario, and it makes matters worse because it messes up the operator control loop as well. It puts the operator out of sync with the BCU. What if the operators develop a habit to release the stick upon contact per procedure? Now note when you're getting this thing into position, when you make contact, that stick is not in the neutral position. When you let go of the stick, even if you're not trying to move it, just letting go of the stick moves the stick. What's that going to do when the boom has not actually been sensed as a coupled situation by the BCU? Well, it's going to command a boom movement unintentionally. You already mentioned the features. We'll skip over this. I think I'll go through these. I don't think we need to belabor the point. Operator believes boom is marginally erratic, maybe not yet near structural limits. Maybe that's why they don't provide the BCU off command. They see it moving around, but they say it's not that bad. That might be one reason. So how do we know that the movement is erratic, not just outside the position range, but the rate of movement maybe is beyond structural limits? They don't have a rate feedback. So they might not know that it's about to break off. They don't have the information to know. All they can see is it moving back and forth. Is that too much, or is it fine? Operator believes they need to regain. This is interesting. If you're a tester, there's a common mindset that if something malfunctions during a flight test, which is what we're talking about, find the cause. Maybe that's why they don't turn it off right away. They're trying to find what went wrong. We can all think of some procedures to mitigate this. Of course, we want to look at commands provided, but not being executed properly or not effective. All right, so that was STPA. We really went over this inside and out on this exercise. Let's now compare. There's a question in your mind I would have if I were you. Yeah, but how much value did we add? Because the whole beauty of STPA is it makes these things so obvious. So how obvious would it be if you hadn't just done STPA? Well, it is interesting to look at some previous events. There was an event in 2016. Here's what happened, and you tell me how close this was to the scenarios we just identified. The boom operator lowered the boom. The boom immediately began to move erratically, well outside of its structural limits. The boom operator could not regain control no matter what it did. The system continued to oscillate back and forth. They declared an in-flight emergency. This is a massive boom. It weighs tons. The boom fully detached from the fuselage and landed in an empty field. $6.5 million lost. In the official cause report, this sensor provided boom control unit with inaccurate position indications. Did we get that somewhere? As a result, the BCU compensated with lateral movement commands to try to stabilize. Did we catch that somewhere? The boom oscillated violently. The components and structures became so damaged that they failed and triggered multiple warning lights. I'm going to pick this apart. This is just a statement that they had. The boom operator's failure to turn off the boom flight control switch in a timely manner was a cause, according to them. We wouldn't word it that way. We would find real reasons why the boom operator might not want to turn it off like we just did. But that is what happened. They did not turn off the boom flight control switch. It continued to oscillate and ripped itself apart. We just 2 seconds ago identified all the reasons why they wouldn't do that. The human reaction time, we're talking seconds. That's not enough for a human to respond and figure out the right action. These are testers that we're talking about. If something malfunctions, they're trying to find the cause. There's inadequate feedback to give them an advance indication that you're about to hit the structural limit. So yeah, they probably saw the thing moving left and right. Did they know that the thing was about to break off before it did, or that it was just erroneous movement that we need to figure out? Turning off the boom flight control switch would have disabled the BCU, would have neutralized the boom flight control systems, would have prevented the boom from departing the aircraft. So much hindsight bias baked in there. But compare that to the scenario we had. Our scenario actually goes deeper than the actual accident report. It shows why the boom operator would think it's the right thing to do. And we didn't even have the accident in front of us. The accident report goes on, in my opinion, the flight control surfaces were erratic and the boom operator should have begun the flight controls do not respond to command inputs checklist. There was a checklist for erratic control surfaces and he did not follow it. If he followed it, he would have turned off the flight control switch, which is step number 3, before the hoist cable and all kinds of other things broke. And there's a checklist. Boy, some of the folks on the line from aviation can probably pick up on a lot of similarities here to other events that are in our mind. Now compare that to a human view that we have crafted. And here's what the boom operators actually said during the event. The boom operator said, the boom is going crazy right now. It's moving left to right past 30 degrees. I don't know what to do, honestly. I have no control over this boom. You can just imagine them trying to regain control over the boom. Of course, if you hit the off switch, that's not regaining control. That's turning things off and it's a dead weight. They're in a different mindset. They're trying to figure out how to get control back over this boom, get it back into operation. Now, meanwhile, this is what's happening to the operators. Now watch this. As engineers, look at the decision that was made way before this point. Hey guys, we can use a single sensor, and this is true, to sense boom roll and send the signal to the BCU. Those load sensors, it's a single sensor for this one here. And this is, and that, now obviously engineers know about single points of failure. Why didn't they catch it? Well, the argument was this is not actually a single point of failure. After all, if it fails, the operators will just disable the BCU. There are so many similarities here. And then, of course, when we do a failure assessment of that component, it's not a big deal anyway because the failure is extremely unlikely. We replace this thing all the time before it fails. The probability of this thing failing is very, very low. Just about every accident report, this is what happens. And then when you look at maintenance, in hindsight, this is what you find. Well, actually, that may not be true because maintenance personnel did not perform step 17, which instructs the maintenance personnel to conduct a polarity test, move it on a dolly and move the aircraft left. And if they had completed those steps, they would have detected the faulty component 17 days before this particular mishap. What does this maintenance activity say about all these assumptions up here that engineers were making? And what does this behavior by the boom operator say about these assumptions that engineers were making? This is why STPA does not depend on a probability assessment, because you may not know it, and even if you think you know, you might be wrong. There are all kinds of other systemic factors that are not baked into the computation a lot of times. You may not think it's a single point of failure, but that's not how STPA works. STPA says, you know what? This is worse than you think because the operators are not actually going to disable the BCU, and here's why. Here are the 5 reasons why they're not going to do it. Now, do you want to put controls in place or not? And here's why a single sensor is not good enough. Not just the failure argument, but we have no ability to detect these glitches in the signal. That was one event. Here's one more. I've just got one slide on this. This is a completely separate event with a different aircraft. The ARO made contact, but the system didn't recognize it. So it remained in free flight mode, which is the manual mode, while it was in contact with the aircraft. the ARO, seeing on their screen that the thing went into contact, released the stick like they always do. But the computer is still in manual mode. And what does it do when you release the stick in manual mode? It sends a command. It moves the boom. It sends large movement command to the boom. And when you're in contact, that's a bad thing to do. The receiver wasn't exactly at its home position or its trail position. So what happened is now loads built up and it broke the tip off. This movement, while it was connected, broke off the tip of the boom. That's a massive problem. It flew and struck the receiver tail of the aircraft. The receiver then commanded disconnection, which was sensed, how? By a pulse that toggled the boom to go to contact mode, even though it was now broken off and in free flight mode. There was nothing to attach it anymore. It just toggled to the wrong mode because of the way the pulsing works. Now the boom was sensing air loads in real time because it wasn't connected to anything. And what did it do? We had this exact same positive feedback loop. It sent a fly up command. It struck the tanker fuselage, lost a fin, became unstable, and departed the aircraft. Whoa! How much of this did we anticipate? I think just about every single bullet, we can go and find entries from you in the live polling that covered many, many times over. And if we look back at the control measures that you would put in place, now there's design measures, there are administrative, procedural, and others that we could put in place. It would be a lot better. This is not as bad as it may sound. The aircraft landed, it was fine. It was an event we wouldn't like to happen, but this was flight test. And this was an incredible recovery. It's also very, very fortunate that this was discovered during flight test. Can you imagine if these flaws were not uncovered and this exited flight test? That would be the failure. This is a success of flight testing. We didn't lose the aircraft. We didn't lose our people, and we found what's wrong with the system. Now, there's always ways to improve. It would be lovely if we could find this even earlier, and maybe you have found a way to do that. It's in a lot of standards. You'll see later. This is my last slide. We'll end. Look at that, right on time. If you want more information about STPA, look at the STPA handbook. Feel free to send an email.